This is the first lecture in Chapter 7, dealing with work. And up to this point, we've been looking at mechanics. We've looked at kinematics, which is the empirical study of motion, just trying to fit equations to the motion that we see in our everyday world. And then we progressed into dynamics, which is the study of motion and the causes of that motion, which is indeed forces. Well, there's other ways to look at motion. Another way that we'll look at later on is one dealing with momentum, and that's really the approach that Newton introduced. But in these next two chapters, 7 and 8, we're going to introduce a way to look at these mechanics problems using energy. And if you can master these two chapters on energy, it'll take you a long way towards understanding mechanics in general. A future course that you might take in classical mechanics will focus in on this energy approach. It's a simpler way to look at more difficult problems. And so it's a very good thing to master. So let's look at energy. Energy is present in the universe in various forms. There is mechanical energy, which we're going to focus on in this course. We have electromagnetic energy, the energy of electric fields, magnetic fields, electromagnetic waves, light. We'll focus on that in Physics 2 and Physics 3. Chemical energy, the energy of chemical bonds, say between molecules and atoms. We can have thermal energy, energy of heat exchange. Nuclear energy, a very powerful form of energy, the nucleus of the atom, what holds the atom together, very strong force, and a lot of energy present there. Theoretically, one form of energy can be transformed into another form. Conservation of energy. We'll make this statement: energy is neither created nor destroyed. It is simply transformed. This is the first law of thermodynamics. It's a law of nature. And as a law, that means it has no exception. No one has found any exception to this. Energy is neither created nor destroyed. So all the energy we have in the universe right now is the energy that we'll have in the future, and it's not going to change. The amount of energy is still going to be there. However, when it is transformed, it's always transformed to less useful forms. So whatever energy we have, when it goes through a conversion, the universe as a whole is going to become less useful. And this is also a law. This is the second law of thermodynamics. We're not going to look at these two laws of thermodynamics too much in this course, but we are going to refer to these ideas. And the idea is energy will be conserved, and when it's transformed, it's always transformed to less useful forms. These are laws of nature. What that means is over millions of years, over billions of people making observations over the course of their lifetime, billions of observations. Through all these billions of observations, billions of people, millions of years, not one instant has seen a violation of these laws. Because if you see a violation of these laws, you have to throw them out. And they're not thrown out yet. Or else you have to modify the law for that one exception that you found, and they don't have those modifications. So these are powerful laws. Every once in a while you hear about somebody who invents a machine, and they say, well, this machine takes in a certain amount of energy, and it puts out more energy than it takes in. Well, such a machine would violate both of these laws, and hence, if you were the patent office clerk, you would just say, reject it based on the two laws of thermodynamics. I'll refer you to a very good website. It's called the Museum of Unworkable Devices. So Google that, the Museum of Unworkable Devices. And if you go there, it's a wonderful website where it shows plans for all these different machines They might be levers, dealing with magnets and gravity, things that you think might produce energy or steal energy from gravity over time, something like that, and they just don't work. All right, and so the challenge is to try to explain why they don't work. But ultimately, it's because somehow they violate these one or both of these laws. So no violation of these principles has ever been found. If you find a violation, let me know. I want to become famous with you. Work done by a constant force. Work is the force times the displacement in the direction of the force. So let's say work is equal to force times displacement, or force times distance in this case, in the direction of the force. So if you're to push this block, or if Einstein were to push this block in one direction, as you're looking at it, for some distance d, the work would be equal to force times d. This woman is pushing a lawnmower, and she's pushing it along the direction of the handle. So there's two components to her force. There's a horizontal component, and there's a vertical component as she's pushing on the lawnmower handle. Only that component of her force that is in the same direction that the lawnmower is moving is going to do work. So only the horizontal component times distance will equal the work that she does. The other force, the vertical force, which is pushing the lawnmower towards the ground, is going to do no work because the lawnmower is not going to move in that direction. So because there's no displacement in that direction, there will be no work, and hence that force will be wasted force on her part. So the work is zero if the direction of the force is perpendicular to the actual direction of the motion, and the work is zero if the particle does not move in that direction. So really, only the component of the force in the displacement direction will contribute to the work performed. So we need to modify our first analysis. Well, we kind of said that force had to be in the direction of motion. So here we'll write it this way. Work is equal to force times distance times the cosine of the angle between the force direction and the displacement direction. If they're both in the same direction, then this would be the cosine of 0 degrees, which is 1, and it's just simply force times distance. But if the force is directed downward like this, we need to take the component of that force, F cosine theta, and then use that as our force doing the work. So the work is positive when the component F cosine theta is in the same direction as the displacement. The work is negative when this component is in the opposite direction as the displacement. I'll give you an example in a moment. Work is zero if the direction of the force is perpendicular to the direction of motion, and the work is zero if the particle does not move. So, I have a box here. Let's say, for instance, I push on this box, and I start pushing on this box like this, and sweat starts pouring down my brow, and I push on this all day and all night, and it doesn't move. If it doesn't move, then officially, by physics, we would say that I've done no work. I have to move it some distance d, before I can have a value of work, at least in a physics sense. So it's got to move. If I push on this block from this direction and it moves in this direction, I'm still doing no work because the force I'm applying is perpendicular to the actual direction of motion that it's going. If I push on this block for some distance like this, I do work. But if I push on this block and you push on the other side like this, and as I'm pushing on this, that actually you're stronger than me and you push me off in this direction, then I would do negative work because I'm applying a force this way, and the actual displacement of this block is in the opposite direction. So there's an angle of 180 degrees between my force and the displacement direction. 180 degrees there between those two vectors. And that means the cosine of 180 is a -1. So I would do negative work while you're doing positive work on the block. Work is a scalar quantity, and it has units of force times distance, Newton meters. Or, this is used so common in our system that we have a name for a Newton meter, or our quantity of work, and that's called the joule. Joule is a quantity of energy, and so we'll be using joules for all the quantities of energy that we're going to look at in the next two chapters. All right, so if I had a box here, and I lift this box up against gravity, I would have to apply a force equal to its weight, at least. And so if I lift the box up like this, I'm doing work against gravity, equal to mg times whatever distance I move it up. That'd be positive work. If I were to lay this box down, I would actually do negative work, because I'm applying a force against gravity upward, mg, and then the actual displacement is going down, which would be a negative displacement, or 180 degrees between the two directions. And hence, cosine of 180 is a -1. I would do negative work. So positive work against gravity, negative work against gravity. If I were to carry this along a level plane like this, holding it up against gravity, but not really supplying an impetus of force along the direction, just carrying it along, I would do 0 work, because perpendicular force and the actual displacement. Interesting. So let's say that I'm going to move this Saturday, and I call up all my friends and I say, come help me move on Saturday, and if you do work, at the end of the day, I'll have pizza and suds for everyone. Suds being my term for either beer or soda pop. So, pizza and suds if you do work for me on Saturday by helping me move. Great. So all my friends show up, and I kind of watch them, and as they're picking up boxes and stuff, I see them, they pick up boxes, and they carry them away, and they load the truck, and we drive to a new location, and they pick up boxes, and they carry them, and then they load it into the new place of residence. And I watch this all day. And then finally, everything gets moved, and at the end of the day, they all come around and say, Dr. Golben, because all my friends refer to me as Dr. Golben, maybe. They say, where's our pizza and suds? I've been eating pizza myself. I've been watching everything happen. I've been munching on a few slices of pizza while things have been going on. And so they come to me and they say, where are our pizza and suds? And I say, well, technically, and this is the way I always talk when I'm trying to bring out a scientific point to my friends, technically, you did work when you lifted up the box. And I appreciate that, because that was positive work. But when you carried it, you did 0 work. And then eventually, when you put it down, you did an equal amount of negative work. So, in total, you did a total work of 0 over the course of the day. So, I'd like to give you pizza and suds as a reward, but you did 0 work on the day. And I told you, pizza and suds if you did work. This is why no one will ever help me move. And this is probably why I have no friends. No, I'm just kidding. So, don't do this to your friends. But if they want to do work, one way they could do work is they could lift up boxes and they could just drop them and break everything in your boxes. But they would do positive work in that way. Or if you're moving from a first-story building to a 2-story building and you moved everything upstairs, they eventually would do positive work in that sense. So that's one way to do positive work. Or just push everything along the ground, you would do positive work. So those are different ways that you could actually do positive work if you were helping somebody move. Just keep that in mind. So let's do a calculation. We're going to put Newton to work. A horizontal force of 150 newtons is used to push a 40 kilogram box 6 meters on a rough horizontal surface. If the box moves at constant speed, find the work done by the 150 newton force. Work is equal to force times distance, cosine of the angle between the two force and displacement direction, in this case 0 degrees. They're in the same direction. So we'll have 150 newtons times 6 meters, cosine 0, which is 1, 900 joules of work. Newton pushing this does 900 joules of work. What is the work done by the frictional force? Well, we're told that this box moves at constant speed. Anytime you see the words constant speed, you should recognize that the acceleration would be 0, the total acceleration, and the net force should be 0 as well, if there's 0 acceleration. So if the net force is 0, all the forces are canceling out, and whatever force Newton is applying on this box, the frictional force is meeting that same force in the opposite direction, giving you a net force of 0 and moves at constant speed. So the frictional force is equal in magnitude, opposite in direction. We would say, at least in magnitude, the frictional force is equal to the applied force. And since the box is moving in this direction, but the frictional force is in that direction, the displacement's this direction, so there's 180 degrees between the frictional force and the displacement. Cosine of 180 is a negative 1. So the work done by friction will be 150 newtons, 6 meters, negative 1, a negative 900 joules. So the net work done on this box would be 0. So you're pushing on it 900 joules of work, friction is pushing on it, negative 900 joules of work, total work 0 joules. Alright, so we introduced this concept of work, force times a displacement. If we were to graph this, force is a function of x with a constant force. It might look something like this graph right here. Just a rectangle. You've got a constant force, constant for displacement d, and we would say the work is force times d. So it's actually the area of this rectangle, the two sides of the rectangle. So the work would be the area contained in this rectangle, and if this were actually a function, a graph, with a constant force as a function of x, then the work done would be the area underneath the function. Well, when you look at the area underneath the function, you think integration, and you would be right. Let's consider this if we had a varying force. Let's say you had a varying force as a function of x. So the force is not constant, it's changing all the while, and you want to calculate what is the work done by this varying force. Well, you might approach it as looking at every little interval of dx, delta x, a small interval of delta x, and over that small interval you might think of a displacement delta x, and the force being almost constant over that little interval, so that the area of that rectangle over that little displacement delta x would be the work done over that displacement. And if you added up all these rectangles for all these delta x's, you would get the work done for any particular total displacement of this varying force. So you add up all these rectangles over infinitesimal delta x, and the work done would be the summation of all these force x's times delta x's. But as your delta x approaches infinitesimally small, then this summation of force delta x becomes a definite integral. So the work is going to be the definite integral of your function of force x dx over from your initial to final x value. And dx is your infinitesimal interval of displacement. So we just have to integrate the force over dx to get the work done by that force. we need ourselves a varying force, and a good varying force is the spring. For a good spring, the force varies as a function of x. It's equal to a negative kx, where k is a constant. K is an intrinsic property of that spring. Here's a spring, and what we're saying is that if the spring were to establish an equilibrium position, as you pull on the spring and pull it further from equilibrium, the force gets proportionally larger. That's trying to restore it back towards that equilibrium. So the negative sign is the restoring force back towards equilibrium. Or if you were to push on the spring, it would also try to restore it back towards equilibrium. And it'll get larger and larger the more your value of x gets further away from that point. So it's a proportional to the x, and this proportionality, this k constant, is the intrinsic value of the spring that you have. So for different springs, you'll have different k's. This is called Hooke's law, and it's a characteristic of good springs. So if you were to push on this spring, you would exert a force equal to the spring force, and the spring force, graphed as a function of x, will look something like this. Negative kx will be a line going down with some slope, negative k. The area underneath this graph will be the area of this triangle, and that's going to be 1/2 the base times the height. So that's going to be 1/2 times x times the height, which is the value of kx. So that's going to be 1/2 kx squared. So the area of this under this force versus x graph is 1/2 kx squared, and that would be the work done. Or another way to get this is if you're pushing on this with some force kx for some distance from 0 to x, then if we integrate that, k being a constant, take it out of the integral, we would have the integral of x dx, which you know to be 1/2 x squared. So we have 1/2 kx squared. Evaluate from 0 to x, which is simply 1/2 kx squared. So that has a work done on a spring in either compressing or extending it a distance x. More on this later. We're going to get back to the springs in the next lecture. But for this lecture, we'll leave it at that. We're also interested in what we call the scalar product of two vectors. Whenever we get to a point where we need to introduce mathematics, the reason is because we want to look at more physics. And we've actually introduced this concept of work, and it's actually related to what we call the scalar product. So what is the scalar product? Well, if we have two vectors, A and B, the scalar or dot product, the operation of this dot product between these two vectors is equal to the magnitude of A times the magnitude of B times the cosine of the angle between the two vectors. In a sense, we can see this as projecting one vector on the other vector and finding what they have in common. If I look at vector B here and I find its component that's actually in the direction of A, that would actually be B cosine theta. So B cosine theta times A is the dot product or scalar product. And it's really extracting what B has in common with A. Or vice versa, if I were to project what A has in common with B, looking at the same triangle or a right triangle, I would have that A being the hypotenuse of that triangle. This side is A cosine theta, and A cosine theta is what's in common with vector B. In other words, the dot product is A cosine theta times B. Either way you look at it, it's the same. A times B cosine theta. This dot product is commutative, which means that A operation dot product with B is equal to B dot A. The dot product is distributed, so A dotted with two vectors, B plus C, you can distribute the operation to the two vectors. So that's equal to A dot B plus A dot C. If A is perpendicular to B, then the dot product will give you 0, because that will be equal to A times B cosine of 90 degrees for perpendicular, and cosine of 90 is 0. And basically saying that if they're perpendicular, they have nothing in common. A is going this way, B is going that way, nothing in common, dot product is 0. If A is parallel to B, they have everything in common. If they're parallel, cosine of 0 is 1, and A dot B is equal to A times B. Hence, for unit vectors, if you had the dot product between unit vectors or themselves, they have everything in common. So a unit vector I dotted with a unit vector I would be magnitude 1 times magnitude 1 times cosine of 0, which is 1. So it would be 1 times 1 times 1, which is 1. So the dot product of a unit vector with itself is 1. Same thing for j dot j and k dot k. The dot product of any unit vector with any other unit vector is 0, because they're mutually perpendicular. So there's always going to be a cosine of 90 degrees in there, which gives you 0. It'll be 1 times 1 times 0, which is 0. Hence, if you had two vectors, A and B, in unit vector form, I, j, k, and you dot product these two together, only the I dot I, j dot j, and k dot k terms will survive. Everything else will be lost. So the dot product between two unit vectors, or two I, j, k vectors, is ax, bx plus ay, by plus az, bz. Everything else is lost. And this will give you a scalar number for the dot product between these two vectors. So this is a different way of expressing the dot product. Let's try this out. We have two vectors, A dotted with B, so we have A is 4i plus 6j, dot that with B, which is 2i plus 3j. What's the dot product? Well, the dot product is distributive, so we have 4i dot with 2i and 4i dot with 3j. And then we're also going to have 6j dot with 2i plus 6j dot with 3j. So we have all these terms here. We know that any unit vector dotted with any other unit vector is going to be 0 because of the cosine 90. So for the second term here, we have 4 times 3 times 0. That's going to be 0. And for this last term here, we'll have 6 times 3 times cosine of 90, 0. I'm sorry, this middle term, 6 times 2 times cosine of 90, which give us 0. And what we're left with is a 4 times 2 cosine of 0, which would be 4 times 2 times 1, or 8. And this last term will be 6 times 3 times 1, or 18. So we have 8 plus 0 plus 0 plus 18. The dot product of these two vectors is 26. You're always going to get a scalar number from a vector operation, the dot product. Taking these two expressions for the dot product, combining them, we can solve for angle theta, and we'd have that the theta angle between these two vectors is the inverse cosine ax bx plus ay by plus az bz over the magnitude of A times the magnitude of B. It's one way to find the angle between two arbitrary vectors in three-dimensional space. So if you didn't have your trusty protractor in your pocket, if you have two vectors in three-dimensional space like this, just take the dot product between them and of either version, solve for the angle theta, and that will give you the angle between these two vectors in three-dimensional space. Good to have. So with this definition of this mathematical operation called the dot product, we can now define work as the dot product between the force and the displacement. Work is equal to vector force dotted with vector displacement. In magnitude, that's equal to magnitude of the force, magnitude of the displacement, times the cosine of the angle between their two directions. So, work is a dot product between force and displacement. Pretty neat. If this was our only use for the dot product, then we might not even introduce the dot product. But there are other things that we're going to use with the dot product, and namely one of them is power. The average power is the work divided by time. For instance, this person working, applying a force over a distance 1 meter would be 1 joule of work, but it really depends on how fast he performs that work. If he does it really quickly, then that's more power than, say, if he takes all day to do it. So it depends on how much work you can do in how much time, and that is power. If you were to do 1 Newton of force for 1 meter and you did it in 1 second, that would be 1 joule per 1 second, or 1 watt of power. Energy can be bought as a kilowatt hour. So if you multiply power times time, you get work or energy that you can buy. Work is power times time. Instantaneous power would be the instantaneous amount of work in an infinitesimal amount of time, dt. We know work is force times displacement, so if we have force dotted with displacement, we have force dotted with a infinitesimal displacement, ds. Did that in an infinitesimal amount of time, dt. ds dt is actually velocity. So power is actually the dot product of force with velocity. How about that? So if you had force and velocity in the same direction, then the force times that velocity times the speed would be equal to your power. In the British system, 1 horsepower is 550 foot-pounds per second. So if you were moving a pound 500 feet per second, you would have a horsepower, and that translates to 746 watts in the SI or metric system. Let's try this out. An elevator has a mass of 600 kilograms, carries a maximum load of 200 kilograms. A constant frictional force of 4,000 newtons retards its motion upward. What is the tension force in the cable? So we have an elevator. It's going up. It's got a certain amount of weight, and there's a certain amount of tension, and there's friction. So we got tension pulling it up, friction against the motion, and weight against the motion as well. And it moves at constant speed. So the tension force will be equal to the two forces opposing it, the frictional force and the weight. That'll be 4,000 newtons plus the weight, which total weight would be the total mass, 1,800 kilograms times 9.8. We have a tension force of 2.16 times 10 to the 4 newtons. Nice to know. What is the minimum power delivered by the motor to lift the elevator at a constant speed of 3 meters per second? Well, we got this force is what we need, and if we're moving at a velocity of 3 meters per second, the power would be the force times the velocity. And they're in the same direction, cosine 0, so it's simply force times speed in this case. 2.16 times 10 to the 4 newtons times 3 meters per second. Everything's SI system. That'll give us 64.9 kilowatts. So we need a motor that can put out a power, a work per time, of 64.9 kilowatts. That concludes our first lecture in Chapter 7, dealing with work and power.